Hi, welcome back. Sorry about last night. It was a marathon session. We're going to make today's shorter. I can't say significantly shorter, but it's definitely going to be shorter. In the end of chapter 17, we're going to be taking a look at the fact that electricity, much like gravity, is a field force. And we're going to make some comparisons between the two. Now, it was Michael Faraday, a British scientist, that came up with the idea of this electric field. Kind of like how we know that gravity is a field force because there is no contact required in order to exert that force. The same thing is true for electric charges. You don't have to come into contact with it in order to have that force of attraction or repulsion on those charges. And so Michael Faraday came up with the idea that around electric charges, so if this is your electric charge, there is an electric field that surrounds it, much like the gravitational one. Where this gets tricky, though, is the fact that where gravity is only an attractive force, the electric force can be either attractive or repulsive. And so the problem lies in the fact that, well, it could be away or it could be toward, depending on what you're talking about. And so Michael Faraday was the one that had to come up and define that. And we've taken his convention. What he did was that he came up with this idea, this concept of a test charge in order to define what the electric field is. And so what he did was he said, all right, I'm going to say that this is a positive charge. And in order to define or be able to illustrate that electric field, he would take a little tiny positive called a test charge and say, all right, what would happen to that charge? Well, we know from Paul Abdul, opposite attract, electric repel, that these positives, this charge would cause it to repel away. And what we're talking about, we're looking at what would happen to the little tiny blue test charge, not what happened to the big black positive charge that we're finding there. Because we're trying to find the electric field generated around that positive charge. And so whenever you are defining the electric field or you're looking at what the electric field is, it's always going to be in terms of a positive charge. Very important to remember, okay, what would happen to a positive charge if you put it there? Now, real quick, I'll slide this down because what happens if we put a negative charge here? And let's go back. If we change this to a negative charge, it's still going to be what effect it would have on that positive test charge. It's just now we put that positive test charge here. Now my electric field lines would come in because it's going to attract that little tiny positive test charge. And the reason he did this was in honor or in homage of Ben Franklin, because Ben said, hey, we're going to assume that it's the positives that move. And so Michael Faraday said, oh, okay, then we're going to define all this electric field as if what would happen to a positive charge would it be there. Okay, and so what you need to remember is if you're looking at a positive, it's going to follow these electric field lines. If you're looking at a negative, it's actually going in the opposite direction. Okay, so we can say that the direction of the electric field is the direction that a positive charge would move. We're going to define it all in terms of that. Now, the magnitude, he actually defined it the exact same way that we defined our our gravitational field strength. Our gravitational field strength, for comparison, okay, you can put this down, but you don't have to have it. Our gravitational field strength was the force due to gravity per unit of mass. We're going to define the electric field strength in much the same way. The electric field strength, which has the symbol capital E, is equal to the force of the electric charge on a particular charge. So that should be an F sub E. There you go. Okay, so this is how we're going to define the magnitude of that electric field. Once again, just like gravitational fields, electric fields are vector quantities. So they have both size and direction. The difference between gravity and electricity, though, gravity is only attractive. Electric fields can be attractive or repulsive depending on the charge. Now, if there's more than one charge, we'll have to add them vectorially. And let me just show you that really quickly. If I have a positive charge here and I have a positive charge here, and I want to say, hey, what would happen to a little tiny test charge if I put right here? Well, the electric field from this one goes in this direction. The electric field from this one goes in this direction. And so what would end up happening is we'd have to add these two vectorially. Wow, that's really lagging. Give me a second here. Let me change this color. I don't think I like it. Add vectorially. So what we would do is we'd add them head to tail. So we would take this red one, and I'm just going to pick it up at this, and we're just going to attach it up to here like that. And so our end result would be an total electric field strength of this. And so what I did was I took this piece and moved it up to there and attached it to this piece. And so our vector result would be straight up. So if we were to put a positive test charge there, it would actually be pushed straight up. We're going to, tomorrow in class, we're going to draw all of the electric field lines that you will potentially have to draw on the Regents exam or on my quiz. I will give them to you all, and we'll talk about how you draw them and what we do with them. Now, when we draw these electric field lines, there are 3 summary points we have to remember. First off, the field lines indicate the direction of the electric field. That's basically it. So they show the direction that a positive charge will move. And so you can actually just look. Field lines indicate the direction of the electric field, and that shows the direction of force. On a positive charge. And we'll examine these and explain them more in depth tomorrow. The second thing is that the lines are drawn such that the magnitude of the electric field is proportional to the number of lines. This is the exact same thing as with our gravitational field. If this is our positive charge, our electric field lines spread out like this. They show the direction of positive charges will move. And what we can say is that the closer together the lines, together, there we go, together, stronger the field. So exactly what we talked about with gravitational field strength. The closer together the lines are, the stronger the field. So here we had 3 lines, here we only have 2. So it's going to be weaker further away. And the last one states that the electric field lines will always start on positives and end on negatives. And this is, again, because of that test charge. Because of the positive test charge. That was just by definition. He could have picked a negative, but he didn't. So these are just the conventions that we live by. Okay? And then the number of lines starting or stopping it gives you an evaluation of how big the charge is. Bigger charges will have more field lines. Smaller charges will have smaller field lines, or not smaller number of field lines. Now, we're going to, in the next couple chapters, talk about moving charges. And the charges move because there's a force on them. There's a reason there's a force on them is because there's an electric field. And so we're going to talk about what happens in a static situation, or what happens if there is an electric field there. Well, if you have a conductor, charges are allowed to move. And so if the charges are not moving, then there's 0 electric field at that point. So some consequences of this is that if you have a conductor, charges will build up on the outside of it. That's the first one. Charges will build up on the outside, on the surface. The second thing is, if there's a spherical shell, charges you'll have an electric field inside the shell itself. So let's say here's your shell. Let's make it a rectangular thing. If I have an electric field that goes like this, there's no electric field, and I'll put that here, there's no electric field inside of that conductor. Okay? And again, I'll go through this in more detail tomorrow as well. So I just want to give you the bare basics. And also, is the electric field lines must always be perpendicular to the surface. And so if I were to draw a circle, if I were to draw a charge, my electric field lines have to be perpendicular to the surface. And sometimes I get sloppy when I draw, okay? But you have to remember that it's always going to be perpendicular, because if it wasn't perpendicular, then there would be a horizontal component to that electric field line, which would cause charges to move. Okay, and I'll explain that in more details as well. Yeah, let me take that positive. Okay. The thing that's going to show all this, and I'm going to break it out tomorrow so you can see it in class. It's called the Graaff Generator. It's an instrument that will show all of these things. And basically it allows you to build up static electricity and allows you to show the field lines on there and how they exert. Okay? And so this is kind of a picture of what happens. You have a rubber belt that's kind of running through. It's picking up electric charges, kind of like scuffing your feet across the carpet. But then it takes those charges up top and distributes them around the top shell, the top sphere. So we will play with this and we'll examine all of those other things in a little bit more detail to hopefully clear up some of the confusion that I know is currently going on. We'll do that tomorrow. So everybody have a great night. We'll see you later. Bye.